Okay, welcome. This is the week 7 webinar. So we're on the second half of the class now. And today is actually really important in terms of what we're talking about. So as always, I'll answer any questions you have. Feel free to pop in the chat box, any questions. And then we're going to go on to hypothesis testing, which is pretty much what we're doing for the rest of this entire course. We're looking at hypothesis testing. There's going to be special kinds of it. We're going to have hypothesis testing about something that may not seem like it until we do it. But every week for the rest of this class, we're going to be using what we're talking about today. So that's really, really important. And in fact, everyone learns about it in middle school, but you just don't call it hypothesis testing. You call it the scientific method. And you've probably heard of that before if you paid attention when you were in middle school, which doesn't always happen. But so let me tell you kind of the things that we're going to do. And this really is not just the order at which we're talking about today, but this is pretty much the order at which you should do things whenever you're doing hypothesis testing. So the first thing you do is you decide on the null and alternative hypotheses. And that's kind of what you want to test. And then what you do is you say, well, I'm going to do a sample, I'm going to make a test, but things can go wrong. And if they go wrong, what might happen? And how bad might it be? So we talk about that, and that's called the type 1 and type 2 errors. And then after that, we'll look at the type 1 and type 2 error, and we'll say which is worse. And based on that, we'll decide on the level of significance. And then the next step is actually the hard step in the real world, and that's collecting the data. Collecting data takes a lot of work in a lot of situations. And once you collect the data, as you're used to, throw it in the calculator and find what's called the p-value. Okay, and we'll also look at what's called the test statistic. So that all happens from all the stuff we've been doing with central limit theorem. It's all about this probability stuff. P stands for probability. And then we'll say, well, how do we state our conclusion? After you've looked at your data and you take a look at the p-value, what can you conclude? And we'll talk about the wording that you have to use for that. We'll talk about how to interpret the p-value. It's going to be a lot of words. Just a note, today has a lot of words. That's just part of today. And then we'll interpret what's called the level of significance, which on number 4, we talk about level of significance, but then you want to interpret it after you've conducted your data to see what might be the issues and all kinds of stuff. So that is how hypothesis testing works. So then I'm going to kind of finish off with talking a little bit about Project 2. We're not quite ready to talk about the details, but I will tell you the main components of Project 2 will be confidence intervals, a confidence interval, and a hypothesis test. So last week we talked about confidence intervals, and this week we're doing hypothesis testing. We're not quite ready yet because next week we're going to be looking at more than one sample, 2 samples, and we're doing comparison studies. And the project is going to be a comparison study. But we can still start planning and start thinking about it, even if you're not ready to do any details yet. So that is the plan for the webinar. And I want to give you kind of a nice reminder, and that is we are in week 7. 7 is an odd number, and that means that there is no exam this week. So this is a week that you can rest a little bit, and this is kind of a coincidence, but I might as well pretend I planned it. What's special about this coming weekend? You know what's special? Yeah, for Memorial Day weekend, so it's kind of nice to have a little bit lighter weekend than usual. It's Memorial Day weekend, have some fun. Just note, I'm not going to have office hours next Monday because it's Memorial Day weekend. I'm not even allowed to. I'm not allowed to do any official work, even though I'm going to grade and stuff. But I can't have a timed anything for Memorial Day, and which is a good thing. Holidays are important. Okay, so that's just a note, is that no office hours Monday. I probably will not have office hours a week from Wednesday either. And that's because one of my colleagues is going to be away at a conference, and I'm going to have to sub for him during my office hour time. So just note that for next week, it's a light office hour week, because nothing Monday and probably nothing Wednesday either. But Tuesday, Thursday, Friday, I'll still have them. And I'll have them all week this week. So just note that you're welcome to pop into my office hour, on Zoom is great, and I can help you out. Are there any questions about anything? Questions? Okay, if there's no questions, let's start talking about hypothesis testing. And it is really, really, really important to understand hypothesis testing. So let me explain, what do you think the most important statistical analysis was in the last 5 years? Any thoughts? To most people, to the world. At least I think so. And most people probably do too, even if you don't think about it. Any thoughts? Don't see you jumping in. And I always try and bring in real stuff instead of fake stuff. And we're going to talk about the most important thing. It was some years ago, but not like 100 years ago. Okay, so if you don't know, let me tell you. That was the COVID vaccine. So, Pfizer, Moderna, and J&J, they came out with this idea that if they give you this shot, okay, or I guess a pill if it's J&J, but if they give you this shot a couple times, then you're less likely to get COVID. And the big question is, how do they make it so the world trusts them? Any thoughts? What they had to do to get trust so that countries would say, yeah, we'll accept it, and we'll announce it and encourage it to everyone in the country? Because that's what happened. It was about, 3 or 4 years ago. 3.5 years ago, I think it was. Yeah, and the question is, was it effective? But how do you know if it's effective? How do you convince everybody? They're making money for one thing. So that's the thing, is you have to make it convincible and without lying, because, hopefully the people who are ahead of these companies weren't liars, cheaters, and murderers. Because, by the way, if they were and they did that, then they'd probably go to jail. So, that'd be bad, or maybe get killed. So they had to make this happen. So what they did is they tested they knew how many, what percentage of regular people got COVID, were getting COVID. So what they wanted to do is they wanted to say, well, if you get the shot that we've got, that no one's really tried before, or hardly no one, then your probability of getting COVID is less. So what they did is they found volunteers. And they found a bunch. Any guess on how many? Any thoughts? Or maybe because I do, because I read it. Before I got my shot, I read the statistics to make sure that I could trust it. Because I didn't want a shot that, might kill me. So I wanted to make sure that they had done their work right. It turned out they did a sample of 40,000. Okay, they got 40,000 volunteers. So what they needed to do at the time, by the way, in like a few months period, about 4% of adults were getting COVID. Okay, that was at that time. You know, things have changed, up and down and stuff. But at the time, about 4% of people were getting COVID. So what they did is they came up with what's called the null hypothesis and the alternative hypothesis. The null hypothesis is a statement that what I think is correct is not correct, right? So if I'm Pfizer or Moderna and I'm trying to get this, vaccine approved, then what I think is correct is that your chance of getting COVID after you get the shot is going to be less. But what the other guy, okay, what you're kind of debating is that no, it's not less than 4%. The vaccine does nothing for you. You still have a 4% chance of getting COVID. So here is the notation we use, and it's very important that you have this down. And this is the null and alternative hypotheses. The null hypothesis is we don't say H0, we say H naught. Any guess why? Kind of a funny reason. Let's see you jumping in, but there's a reason why we say H naught instead of H0. Okay, the reason is that the British got to it before the Americans. And that's how they say the number 0. They use naught. So it has to do with Britain. They got to it first. So we don't say H0, we say H naught. So H naught still 0 to us. And then so this is really important in the notation. You have to understand this notation. H, and then subscript 0, and then colon. Hopefully you all know the colon. Okay, it's on every keyboard. And then what we're trying to show is a population proportion. Well, what we're trying to show is what we're trying to debate against is the other guy is saying the population proportion of those who take the shot, the proportion who still get COVID is 4% or 0.04. Any questions on H naught and how you write down the symbols for this H naught? H naught colon P equals 0.04. Any questions on that? Okay, and that's when it's for proportions, because P is a letter we use for proportion, for population proportion. And then the alternative hypothesis. And in our class, mostly I'm going to be using H1 because that's the number after naught, after 0. You'll also occasionally see H sub A because that's the first letter of alternative. So I'll usually use a 1, but some people use A also. It just depends on where you happen to be, I guess. And then you put a colon. And what these vaccination companies wanted to show is that the proportion of all people who get the shot and end up getting COVID is less than 4%, or P is less than 0.04. Any questions on the symbols in the null hypothesis and the alternative hypothesis for this example? I will let you know it does change. I mean, this 0.04 is the number will change in almost every example. It turns out P will change when we're not talking about proportions. We'll get that today. But the H naught and H1, that never changes. The colon never changes either. The other thing that can change is this less than sign. So this was an example where you wanted to show that the proportion of people who get COVID after getting the shot is less than 4%. There are other examples where you want to show the proportion is greater than something. Okay, so for example, if when I ran for office, I think I mentioned that I did run for office, and I was on the ballot, and I did a little hypothesis, and my H1 was P was greater than 0.5, because you have to have greater than 0.5 to win the election. Does that make sense? So you'll often see less than, you'll often see greater than. The other thing you'll see is a not equal to, and I'll explain that in a little bit too. Any questions on this? So step 1 is write down the null hypothesis and alternative hypothesis. Write them down in symbols. Okay, do not just write them in words. Any questions? Very important. You're going to be doing this on just about everything we do for the rest of this course. That's how important this is. That's why I've said it like 6 times already. Okay, that was step 1. Okay, step 2 is we're going to state the ramifications of a type 1 and a type 2 error. I want to let you know what I've learned, because I've been teaching this for a long time, is that a big percentage of the class doesn't know what the word ramification means. Sometimes, it's not a math word, by the way, it's an English word, but it's an important one. And I'm going to be, using it sometimes on asking you questions. So the ramifications are the bad things that happen if the error occurs. Any questions? That's what it means to say state the ramifications. Okay. And if errors occur, bad stuff happens, right? Okay, so let me give you a definition. So first is the type 1 error. So type 1 error means that you reject the null hypothesis, but the null hypothesis is true. Okay, so basically you conclude that the null hypothesis is false. I have statistically significant evidence to say, hey, the null hypothesis is false, but I'm wrong. And that's bad, right? That's bad. When you think you're right and you're wrong, that's not a good thing. Okay, in medicine, do you know what they call the type 1 error? Especially for like pregnancy testing. Let's call it that kind of medicine. Let's suppose, you or your significant other thinks they might be pregnant. They take the test. You know what a type 1 error is? Any thoughts? 2 words? Yeah, false positive. Okay, because that's when you took that pregnancy test, okay, or your significant other took the pregnancy test, and it says, hey, plus, you're pregnant. And then you go to the doctor and you find out you're not pregnant. You get the scan, it's like, there's nothing in there. And that's bad, right? Okay, that's a big error. It's not good if you have a type 1 error. Okay, in this case, a type 1 error is pretty terrible too. So for our case, okay, for the case in the vaccination, what that would mean if there was a type 1 error, that would mean that they had statistically significant, I'm going to use those words a lot, evidence to show that the vaccine works. It's wonderful because it works. And then the Federal Drug Administration, FDA, is going to approve the vaccine, tell the whole country to take the vaccine, and it doesn't work at all. That's terrible, right? And I don't know about you, but I got vaccinated and it didn't kill me, but I was so tired the next day. Okay, I was miserable, but it only lasted a day. And imagine if everyone had to go through that and it didn't do anything to help you. Okay, the other thing that it would do is that if you get the vaccination, the other thing I did when I got the vaccination got vaccinated. Then I went and I saw all my friends and family that I was like hiding from because I was worried about COVID and I didn't want to give them COVID or get COVID from them. But once I got vaccinated, I stopped worrying. Okay. On the other hand, imagine if you think the vaccination works, but you were wrong, then you're going to be around all your family and friends and get COVID and then give them COVID. It'd be terrible, right? Okay, that'd be a really bad thing. Any questions on that idea? So those are the ramifications of a type 1 error. Okay. Now let's look at a type 2 error. So a type 1 error is a false positive, right? Any guess on what a type 2 error is? This should be obvious. Type 1 error is a false positive. Any guess on what a type 2 error is? Let's see you typing it in. It's a false negative. It's the opposite of a false positive, basically. So it means there isn't enough evidence to reject the null hypothesis. We say we failed to reject the null hypothesis when the null hypothesis was false. Okay, so in the pregnancy example, because that's an easy one to imagine also, is, you or your significant other takes a pregnancy test and it says, you're pregnant, right? It's got that big plus. You get all excited, you do all the things that, to plan for your baby. And I'm sorry, it says you're not pregnant. Sorry, with the false negative, you're not pregnant, right? And then you say, okay, I'm not pregnant. So, hey, maybe you're going to go out and, drink 5 beers. Because, hey, you're not pregnant. You don't have to worry about it. And guess what? You just killed the baby, okay, or really hurt the baby. Or who knows, maybe you're going to be not preparing for the baby and not ready for when the baby's born. And then all of a sudden you get way pregnant. So that would be bad. Okay, so in this case, there's not enough evidence to reject the null hypothesis. So you fail to reject the null hypothesis when the null hypothesis was false. So the ramifications for COVID is that if we don't have evidence to say that the proportion of people who are vaccinated that get COVID is less than the proportion of people who are not vaccinated and get COVID, which is 4%, but actually the vaccine would have worked. And what would happen is the FDA would not approve it. Okay? Then the vaccine doesn't get approved. And no one gets vaccinated. And if no one got vaccinated when we had a vaccine, you can have another 1 million people die of COVID when they didn't need to. That's pretty terrible. Any questions on that idea? Okay, so if you don't think the ramifications are bad, think again. You can always find bad things for the ramifications. Any questions at all on the idea of what it means to have a type 1 or type 2 error? Any questions? And I do want you to know that I will ask you, what are the ramifications? And you have to talk about the bad things that will happen because of the error. Okay. So again, step 1 was to state the null and alternative hypotheses. Step 2 is to interpret and look at the ramifications of a type 1 and a type 2 error. Step 3 is going to be decide on the level of significance. So the idea here is, if and this is something in our class, but it's pretty standard, but I will let you know you have to do it in our class. The standard level of significance is 5%. Do you remember I mentioned the standard confidence level was 95%? The standard level of significance is 5%. And it turns out that the confidence level was kind of like the probability of getting it wrong. I'm sorry, getting it right. You have 95% confidence in a way, before you even look at anything, before you do the study, there's a 95% chance that your confidence interval will contain the population mean or proportion, whichever you're looking at. Similar, before you collect the data, if you choose a level of significance of 5%, then there's going to be a 5% chance, if you know nothing, okay, of a type 1 error if the null hypothesis really is true. Okay, so the standard is 5%. Now, you might say, I don't want a 5% chance of being wrong. I want to be right more often. So maybe I'll do only a 1% chance of being wrong. Doesn't that sound better? Any questions on that? Okay. And in our class, we're either going to use a 1% or a 0.01, a 5%, which will be the standard, or a 10%. Okay. So it turns out that if the type 1 error is worse, that we're going to use a 1%. If the type 2 error is worse, we're going to use a 10%. Okay, and that's going to be our standard in the class. I'm not saying that's what everyone in the world does, but that's what you have to do. And when I ask you why you chose your level of significance, it should be about which error is worse. Okay, so my feeling for the COVID vaccine, I think the type 2 error is worse. I think it's much worse to have a vaccine and not use it than to think a vaccine works and it doesn't and use it. So if a type 2 error is worse, because, you know, maybe 1 million extra people die if that happened, that's worse. Then you're going to use a level of significance of 10% or 0.1. I will let you know the letter we use is this letter right here, which turns out to be the first letter of the Greek alphabet, which is alpha. And that is the letter alpha. And if you want, by the way, on your discussion post, for example, you can use ALPHA, like you can spell it out if you want. You can also go to the Canvas equation and go to Greek and find alpha, which is the first letter. Those are 2 ways of doing it. For your project, I want you to use the Greek letter because then you get help and lots of time. You have many weeks to do your project. Project is not due until the end of week 11, and we're at the beginning of week 7. So you have more than 4 weeks. So you have plenty of time to go figure out how to do that on, like, you know, if you're using Google Docs, for example, it's pretty easy. In fact, I don't know if you know, but we're in Google Docs right now. And the way you do it is you just go to Insert, and you go to Equation. And then right here, you even see the little alpha. You click that arrow and click alpha. And that gets the alpha. So that's how you do it in Google Docs. Microsoft Word's pretty easy. You can insert equation, go to same thing. And again, Canvas is pretty easy too. So typing the alpha is not that hard. If it's an exam, then you may not have time to think about it and just write ALPHA for alpha. Any questions on that? All right, so the step after deciding on the level of significance, which we decided that it was 10% or 0.1, the step after that is to collect the data, which is actually the hardest step. Collecting the data takes a lot of work. I mean, imagine finding 40,000 volunteers to get a COVID vaccination that no one even knows if it's safe or works or whatever, because they were the first ever to get vaccinated. And getting people to do it is not that easy. Do you agree? In that case? Okay, it's not easy at all to collect the data. Okay, but they did. Okay, they definitely did. I don't know all the details on how it was done because I've looked at the statistics, but I wasn't part of the study. But I will tell you, I was part of one of those studies once. I actually, it's kind of weird, but I was at UC San Diego as a student, and there was an article in our little newspaper that said, "Hey, if you have the runs, run to our medical center. We'll give you, I think it was $100 to, be part of the study." And as you might guess, I had the runs. It was a bad day for me, but I was part of the study. So I got to see what it was like to be part of a medical study. Okay. And stuff happens. So collect the data. And that could take months and months. It could even take years. In the COVID one, it took months because they got to give everyone the vaccine. And then they got to watch them for a few months. They got to keep communicating with these people and finding out if they have COVID or not. Okay, it's not a quick thing to do. So I want to let you know, even though in our class, I'll usually just say, hey, here's the data, or here's the statistics that happened. Go finish the task. In the real world, that's the biggest part, is getting the data. And we've already talked about ways of preventing bias or avoiding bias, using, if you can, stratified sampling. Randomized studies are hard. That's a real tough one to do. All kinds of stuff. All right, so then once you collect your data, then you do what you're used to doing, and that is put it in the computer. Okay, and we'll go over that. Right now, I'm just kind of going over the steps to do things, but then we'll do some examples. We're going to put it in the computer, and we're going to find the p-value. Okay, so I want to let you know we have looked at data, and do you remember when we were in chapter 7? I had you write down some data in the discussion post. Do you remember that? And then you had to reply to your classmate's post. You had to find the probability that, given some assumption, that your proportion or mean, whatever it might have been, was less than or greater than some amount. I don't know if you remember that happening, but that was something you had to do, over a week ago, but not that many weeks ago. And you had to calculate that probability. Basically, that was to get you ready for today. It was the main application of the central limit theorem, which is finding the p-value. Okay, we also use it to find the confidence interval, but the p-value is even more important. So what we did is we set 0.04 as the population mean, because that's our assumption. Our H naught is that the population proportion, is that P equals 0.04. The population proportion is 0.04. So on the graph, we can say that is the mean for the central limit theorem for sampling distributions. Okay, the p-value they found when they did this study was 0.01. Okay, so that's the probability that if it really was a 4% chance of getting COVID after getting vaccinated, in other words, vaccination does nothing for you, then there would be only a 1% chance that this study of 40,000 people would end up with such a small percent getting COVID, or smaller than that amount or less, that's just a 1% chance. And that's called the p-value. And here it is on the picture. Any questions on this idea? Feel free to ask questions. Big part of the webinar. Any questions? Okay. Sorry, they got not a 1% chance. They got a 1% of the people getting COVID, and the p-value was 0.004. Sorry, I forgot to scroll down a little more. The p-value itself was 0.004. That p-value is really tiny. You see that? It's less than 0.1 for sure, because that's our level of significance. And not only is it less than 0.1, it's less than 0.01, which is like the lowest level of significance that you'd ever bother using. So because our p-value is so small, then do you remember in that discussion post assignment that if the probability is that small, then you say the assumption that 4% of all vaccinated people would get COVID must have been wrong. And the way you say it in terms of statistical vocabulary is there is, in this case, strong, because it's actually less than 0.01, statistically significant evidence. Notice statistically significant evidence, I will tell you, if you can't read colors, it is a biggie. Statistically significant evidence, I'm going to say it loudly, because that needs to be in there. Those words have to be in your conclusion. So if you're making the conclusion and you end up with a very small p-value, you have to say there is statistically significant evidence. And then to conclude that the population proportion, that population must be there. Okay, I noticed I just graded the exam and the confidence interval piece for the discussion board. And some of you left out population. Do you know what happened? If you left it out, you know what I had to do? Those who left it out, you know what happened? Let's see, jumping in. I took off points. Okay. If I say something loudly like that, like statistically significant evidence and population, you better put those in. And that's when we call reject the null hypothesis. Means we have a very small p-value. And this word population is there either way. Okay. So we conclude the population proportion of vaccinated people who get COVID is less than 0.04, which is another way of saying the vaccination works. Any questions on that? All right. Because there was strong statistically significant evidence to conclude the population proportion of vaccinated people who get COVID is less than 0.04, the CDC approved the vaccination. And they announced everyone should get vaccinated. And it was the right thing to do. And after that, definitely fewer people got it. Doesn't mean no one got it, because remember, less than 0.04 is not the same thing as 0%. But at least you have a smaller percent chance if you're vaccinated than if you're not. Okay. And then if you wait another 6 months, there was a new strain. Don't you hate that? So the percent of everyone went up whether you're vaccinated or not. But the vaccination still helped. Okay. Any questions at all on the p-value? And the conclusion. This is the conclusion. If I say state the conclusion, this is basically what you state. It won't always be about COVID. If I say interpret the p-value, that is different. So notice state the conclusion starts with there is. Those should be the first two words in state the conclusion. Interpret the p-value starts with the word if. That will really help you get started. Okay, because if you start with the word if on state the conclusion, it's going to go very badly for you. Because that means you're just completely not getting it. So interpret the p-value starts with the word if. In this case, it's if the population proportion of all vaccinated people who get COVID is 0.04, and if another study of, it turned out, I said there were 40,000 people, it turned out 25,000 of them got the real shot, and they did a randomized control study. The other 15,000 got a fake shot and were told they got a real shot. I should tell you that. Turns out how it really worked. It's a little more complicated than I'm making it, and we'll talk more about it next week. Okay, so if another study of 25,000 people were vaccinated and COVID tested during the end of the testing time, then there would be a 0.4%. That's the 0.004, by the way. A 0.4% probability that fewer than 1% of them would get vaccinated. Would get COVID. Okay. Fewer than 1% because that was the percentage of people that were vaccinated that ended up getting COVID. Okay, this is actually probably the hardest part of this whole week, and maybe the hardest part of like several weeks, is truly understanding what this means. We'll do some more examples, but I just want to make sure that you get the idea. Any questions? Since this is really hard, make sure you can understand it, where all these numbers came from. Any questions? Okay, if there's no questions, I'll go on, but you can always ask questions even while I'm talking. Then we want to interpret the level of significance. Okay, it turns out, let's look at the first bunch of words in interpret the p-value. If the population proportion of all vaccinated people who get COVID is 0.04, and if another study of 25,000 were vaccinated and COVID testing during and at the end of testing time, then there would be A. What you will notice, maybe I'll pop in some spaces so we can see it all together. What you'll notice for interpreting the level of significance, it's exactly the same beginning. If the population proportion of all vaccinated people who get COVID is 0.04, and if another study of 25,000 people were vaccinated in COVID testing during the end of the testing time, there would be A. That didn't change. But now the level of significance was 0.1 or 10%. So this is what changes. There would be a 10% probability that we would end up falsely concluding that fewer than 4% of all vaccinated people get COVID during these months. Any questions on interpreting the level of significance? Okay, it is also the probability of a type 1 error. It's a long way of stating it. And if you think you can write either interpreting the p-value or interpreting the level of significance without a lot of words, think again. Okay, there's a lot of words involved in these interpretations. Any questions? Okay. So just to notice, the null hypothesis is what you're hoping to refute. The alternative hypothesis is what you're hoping to find evidence that is true. Okay, so we've now gone through each step of hypothesis testing. The order at which I did things is the order at which you have to do things. You don't have choices. Okay, in your project, you're going to be having to do a hypothesis test It has to be done in this order. Okay, you can be writing a lot more than what I wrote because it's a project of many pages. Okay, this is more for answering questions on an exam kind of thing, because you're going to have to do, full long paragraphs of explanation for the project. Any questions at all on the hypothesis testing? It's very important. And we're going to be, like I said, doing it for the rest of this course. There will not be a chapter that goes by from now on that doesn't include hypothesis testing. Most are all about hypothesis testing. Okay, so let me give you another one. And I'm not sure, again, I don't mention your names, but are you in Tahoe? You can put in the chat box, yes or no? Are you in Tahoe? Okay, you're not. Hopefully have you been to Tahoe? Have you been to Tahoe, yes or no? Okay, so if you haven't been to Tahoe, but then you may not know, but our most important thing in the entire Tahoe area, you ask anyone who lives here, and that is our lake. We have, if you haven't been to Tahoe, you should definitely come to Tahoe because it is absolutely beautiful. And one of the real important things that we have to do is make sure that we maintain the environment well enough so we don't have environmental disasters in our lake, because we don't want our lake to get destroyed. One of the things that we do every year is we take data on the water coming into Lake Tahoe. There are many, many, many streams that go into Lake Tahoe. And I'll let you know, just that was 9 days ago. I was one of the volunteers that went, and by the way, you don't have to be a scientist or mathematician or statistician for this, that went in and I collected the data. One of the things that I collected was the pH, okay? And again, I don't expect you to know anything about chemistry, but you probably heard the word pH before. And pH of water is 7, by the way. So one of the things that you might wonder about is if you look at the water that flows into Tahoe, is the pH 7? Because we'd like it to be 7 because then it's perfect water, okay? Or at least really close to 7. Any questions on that as something you care about? Okay, if the pH is really high, then it's very basic, chemistry basic, and it's awful, by the way. If the pH is really low, then it's really acidic, and that's awful also. If you have over acidic or over basic water that comes in, it is going to kill everything, all the fish and all the native species in Lake Tahoe, which we don't want. We want to protect our environment. So we want to come up with an alternative hypothesis. So H naught colon, it's not going to be P anymore because the pH is a number. It's not a yes or no question. You do a reading and you say, hey, the pH is 7.1 or the pH is 4.3, which would be horrible, by the way, if it was 4.3. Okay. H naught is that mu equals 7.0, which is the pH of water. So the null hypothesis is, yeah, the water coming to Lake Tahoe is truly just water. The alternative hypothesis, H1, is mu is not equal to 7.0. Because again, if it's either way up or way down, that's bad. And we want to find out if we have an issue. Do you see? By the way, H naught is always going to have an equal sign. We're not using P here because we're talking about means. We're using mu. I do want to let you know the not equal to sign, you can find it using equation editors and stuff. You can also write NOT and then the equal sign, and I'll allow that. Not on the project, but on the everything else. The project, I want you to make it pretty because you have plenty of time to get help and all that. Any questions on the null and alternative hypotheses for this particular study? Okay, so for this example, couple things. One, this is called a two-tailed test because it's not equal to. So not equal to means that if it's very high pH or very low pH, then either way, you're going to say H1 is true because that's not equal to 7. So that's why it's two tails, because high and low are the two tails. Okay, let's look at the ramifications of a type 1 error. Remember, a type 1 error means that if the null hypothesis is true, then we're going to end up saying that the null hypothesis is false. So in this case, we're going to say we have statistically significant evidence to show the pH differs from 7 when it really is 7. All right? So we've done all this testing and we're finding, oh my God, we don't have the pH of water. We're going to get the government to fund a huge amount of money to mitigate this pH issue in the creeks. But it never really needed to be done. It was a complete waste of money because the water was fine. That's a pretty bad error, isn't it? Okay, it might be $100 million of cost. And you didn't even need to do it. Do you see how that error works? A type 2 error means there's no evidence to support the claim that pH differs from 7, but it actually does. So in that case, we collected this data and we're gonna say, oh, the water's fine, it's coming in, no problem. We're not gonna get funding because it doesn't look like there's a problem. But the water was terrible. We were wrong. And Lake Tahoe plant and animals will go extinct, which is terrible. Okay, now this is depending on you, and it's, this is all about how you feel. If you've never been to Tahoe and you don't live in it, you may think spending money is terrible and worse than losing creatures in Tahoe. But if you live in Tahoe, we care about the creatures. So we're going to say type 2 is worse. Okay, on the other hand, if you're all about money, then you're going to say type 1 error is worse, and you're going to use 0.01. If you're all about the environment, you're going to say type 2 error is worse, and you're going to use 0.1. Any questions on that idea? If they were kind of the same to you, would be horrible to lose money, and it would be horrible to have species go extinct, then you're going to use 5% or 0.05. Any questions on the choices? Okay, so you make the decision. You got to make the decision before you collect your data, by the way. Okay, that's called ethics. All right, so let's suppose that we did the study. I haven't looked at the data yet. I can ask them, but I don't know if they've given it. But let's suppose that we looked at the study and X bar, the sample mean pH, was 6.4, pH of 6.4. The standard deviation, again, this is sample standard deviation, was 3.5. And the sample size was 15. Okay, which is a pretty small sample size. Okay, sometimes that's all you can do. You only have so many volunteers. so many creeks you can look at or whatever it might be. So let's suppose they only looked at 15. I actually honestly don't remember how many. I was one of the groups that looked at one of the creeks. So I don't remember how many groups, but looked like it was around 15 groups. Okay. So 15 is less than 31. If I ask you what assumptions must be you make, and you don't state that n equals 15 is less than 31, I take off points, which happened, by the way, on the assignment due last week, because I said, what assumption you have to make. You have to explain why, not just give the assumption. So since n is less than 31, we must assume the distribution of pH levels of streams flowing into Tahoe is normal. Because if you don't assume that, we can't do any of the math. Any questions on that? Okay, I'm going to hide this for now. And let's do this. That also. So the next step is to do the calculation. So I'm going to go in here, and what calculator do you think I need to use? Give me the number. What calculator number should I use? So 15 sounds good, but if you look, so 15 is hypothesis test for mean with data. Do we have the data here in this question? We know the data. We have X bar, S, and N. Those are statistics. So we don't want to look at a hypothesis test for mean with data. We want a hypothesis test for mean with statistics, because we're given statistics, not data. Any questions on that? So I'm going to click on that. Is sigma known or unknown? Pretty much, you're never going to know sigma, but some other professors from other colleges asked me to put this in, so I did for them. But in the real world, you don't know the population standard deviation. You only have a sample. So our S was 3.5. Our X bar was 6.4. Our N was 15. Now mu naught, just to note, that is the mean that's stated in H naught. That's why I wrote it as mu naught. Okay? So that's the mean. It's called the hypothesized population mean. I always have instructions at the top, by the way. So hypothesized population mean. And that was 7.0, because that's our mu for H naught. So 7.0. Our hypothesis is mu is not equal to 7. So I'm going to click on not equal to. Any questions on putting the things into the calculator? Then I hit calculate. And just a note, our test statistic is a T. Do you remember last week we talked about confidence intervals? And if you don't know the standard deviation of the population, which you almost never do, then you have to use T instead of Z. Use the student's T distribution instead of the normal distribution, because that was that extra error of using S instead of sigma. So when you're asked for the test statistic, that's this value, T equals negative 0.66394, etc. P is a p-value, which is about 0.5175. So the test statistic, again, was negative 0.6639. And the p-value again was 5175, 0.5175. Just a note, and this is important, over winter break, I made these pictures. So here was H naught. We have a 7. We have a 0.64. And that was the value we found, the X bar. And then if you take the area to the left of 0.64, and you add that to the area, the mirror image of that, that's that right side, so it'll be twice the area to the left, because that right side plus the left side by symmetry is twice the area to the left. That will give you the p-value of 0.5175. So note that the p-value is the area under this distribution. By the way, can the area ever be bigger than 1? Is that a yes or no? Put it in the chat box. Can the area be bigger than 1? And I'm asking this for a reason, a very important reason. Thought? Yes or no? Can the area be bigger than 1? All right, I don't see you jumping in, so I think I'll answer it. P stands for probability. Area is the probability. Probability can never be bigger than 1. If you ever think you have P greater than 1, think again. What that sometimes means in the calculator, especially if you're using a smartphone, by the way, is that it turned it into scientific notation. And sometimes it'll give you like 1.0357, and then you'll see E negative 18 or something. And that means you got to move the decimal place over 18 places. And it's almost really close to 0. So I want to give you a heads up. That's a real common error. And don't make that error. If you ever think p-value is bigger than 1, think again. It can't happen. Okay, so P is 0.5175. So again, that is the area of the shaded region. That's the left side and the right side. Notice I put 6.4 because that was what we got. And then the 7.6 is the other side, because notice 6.4 is 0.6 below 7. So 6.6 above 7 is 7.6. Okay, so the total area of the left and right means left of 6.4 and right of 7.6. So let's look at the conclusion. So the p-value is 0.52 about, which is definitely bigger than 0.1. So here's what we say. There is statistically insignificant evidence. Notice the IN before significant. So the significant means that you have a less than your level of significance. Insignificant means you have greater than your level of significance. So there is statistically insignificant evidence to support the claim that the population mean pH of water that flows into Tahoe differs from 7.0. Notice population. Don't even think about proportion because this is about a mean. I noticed a lot of mistakes on that, writing proportion when it was supposed to be about mean on the exam. Any questions at all on this? Okay, what does it mean to have a p-value of 0.5175? And here's what we do. You kind of start with stating that the null hypothesis is true in words. And that is, if the population pH in all creeks that flow into Lake Tahoe is 7.0. Okay, that's the same thing as H naught is true in words. And if we measured another 15 creeks, that says we're going to do the study again, then there would be a 52% chance, because that's our p-value as a percent, that the sample mean, notice now we're talking about the sample mean from this new study, would either be less than 6.4, because that's what we got. We got 6.4, less than 6.4, or greater than 7.6 because we have a two-tailed test, a not equal to sign. Any questions at all on the interpretation of the p-value? Okay, let's interpret the level of significance. And great thing about this, by the way, if you're typing this out, all you do is go like this. You go all the way to there would be A. You hit Control C, copy, and then interpret the level of significance, and then you just paste that part of it. It's exactly the same. If the population mean pH in all creeks that flow into Lake Tahoe is 7.0, and if we measure another 15 creeks, there would be a, in this case, 10% chance, that's our level of significance, that we would end up falsely concluding that the population mean pH of creeks that flow into Lake Tahoe differs from 7.0 because we have a not equal to, which is here. It is really important that you understand this. If you don't understand it, you're not going to be able to get this right. Okay? And also, if you refer to the population mean when it should have been a sample mean, then I take off points. If you refer to the sample mean when it should have been a population mean, I take off points. So make sure you understand it and you write it correctly. Any questions on this example? Any questions? Okay, here's another example. Let's suppose you want to see if women are not drinking the recommended 2.7 liters per day on average. Okay, so by the way, we're talking about water. Okay, or fluid, let's say good fluid. Okay, then the idea is if they're not drinking this recommended liters, doesn't mean they have to have exactly 2.7, but the recommendation is at least 2.7 liters. If you drink 3 liters, that's fine, not a problem. Okay. I'm going to talk about it, but not write it down. If you think about the type 1 error, that would mean, we did our study or observation. We ended up concluding that women aren't drinking enough, but they're being fine. They're drinking the right amount. They're drinking 2.7. Okay. And that'd be pretty bad. Okay. The other choice is, let's suppose that we did our study and we weren't able to conclude that women aren't drinking enough. Okay. And they're not drinking enough. That'd be bad too. But let's suppose we decided on the level of significance of 0.01. So let's suppose we decided that would mean the type 1 error is worse. So type 1 means that we decided women aren't drinking enough when they really were. We piss all these women off. That would be terrible. Okay. Okay. And the next step is to collect the data. This is suppose I just made these numbers up, but you can imagine collecting data. And let's suppose this is the data we collected. 2.4, 2.8, 2.9, 2.2, 2.8, etc. What calculator should I go to? Which calculator? And look through the calculators and see which is the right one. And I'll jump in and say it. We have data. We're talking about a mean because it's the mean amount of water that is drunk. And it's a hypothesis test for a mean with data. It says put your data in here. Whoops, wrong one. I thought I copied and pasted, but I didn't. Let's try again. Copy. And I'm going to paste the data in. Okay, that would be a lot of work for me to type all those numbers, so I copied and pasted them. Notice it says that type in the population standard deviation if it's known, or leave it blank if it's not known. It's not known, and we almost never know it. For our H1, it was mu is less than 2.7. So we want to make sure it says less than. Our mu naught is 2.7. And hey, calculate. Wasn't too bad, was it? Okay, so now, if you look at this, we have our test statistic is negative 1.94 about. Our p-value is about 0.03. Okay. So had we used 0.05, we would say there's statistically significant evidence to conclude that the population mean amount of water that women drink is less than 2.7. But we use 0.01, so there is statistically insignificant evidence. Do you see how that works? Notice what I do in the picture. Here's our value of 2.54 for what's the value that we got. And notice that it's in the red. In the red means that we're good enough to reject the null hypothesis at 0.05, but not good enough if it were blue. You see how that works? It should be 0.01. It would be good enough if it was 0.1, because, hey, if you can reject at 0.05, you definitely get to reject at 0.1. Any questions on that? So the conclusion, I'm just going to say it because we only have so much time and I do want to talk about the projects, is that there is statistically insignificant evidence to conclude that the population mean amount of water that women drink is less than 2.7. I do have a template for you. And that is, there is statistically, it'll either be significant or insignificant evidence to support the claim that the population, okay, for this week, it'll either be a mean or proportion. And then it's going to be whatever you're talking about. When I write XXX, then it's a whole lot more words. Similarly, p-value, I'll say the interpretation on this. Our p-value is 0.03. So that would mean that if the population mean amount of water women drink is 2.7 liters per day, and if we did another study of how many we have, this many women, then there would be a 3% chance that the new study, you'll notice we have our X bar was 2.54. The new study would end up having a sample mean amount of water drunk by the women being less than or equal to 2.54 liters. Any questions on that? Okay. And the template I have is if the null hypothesis is true, in a lot of words, by the way, in that parenthesis, and if another sample of however many we did was taken, then there would be a, whatever the p-value was, probability that, and then it's the results of the new study would be at least as extreme as the results of this study. But that, of course, you have to write in words about the study and the numbers you got. Similarly, for our level of significance is that if it was true that the population mean amount of water that women drink is 2.7 liters, and we did another study of that many women, then there would be a 1% chance, that was our level of significance, that the new study would end up having us falsely conclude that the population mean was less than 2.7. And I do have a template. And that is if the null hypothesis is true, but if it's in parentheses, you got to put that in the context. And if another sample of however many was taken, then there would be a whatever probability, that's the level of significance probability, that the new study would result in falsely concluding that, and then alternative hypothesis true in words, in context. So don't just copy and paste this and don't change anything. That'd be terrible. Any questions on this? Okay. So here's a question, just a fun one. Do more than 14% of all Americans think their home is haunted? Hey, do you think your home is haunted? Put in the chat box. You think your home is haunted? Drop in the chat box. Is your home haunted? Okay, I don't see typing in, but the answer is either yes or no. Either your home is haunted, or either you think it is or you don't think it is. So when it's a yes or no, then our variable is going to be p, not mu. So p is equal to 0.14, and h1 will be p, and it's more than, so greater than 0.14. Any questions on that? Okay, there was an article I read a while back, I'm not even going to mention it, but they did a sample of 1,017 people, asking them, is their home haunted? And they found a sample proportion of 0.16. So let's see what we've got. So now we're going to go back to the calculator method. And here we had h naught p was equal to something. Proportion, that's really important. If we're talking about proportions, we're doing a hypothesis test. We're going to do the hypothesis test for a proportion. And our n was 1,017. Our x, we look at here, our x was, well, we had our p hat was 0.16. So what I'm going to do is I'm going to go to the scientific calculator, and it's going to be 1017 times 0.16. And note, it says 162.72, but that's not possible. You can't have 0.72 people say yes. So you should always do rounding when you're talking about yes/no questions, and you want to see how many people said yes. So now it's going to be 163. And a group of you made that error on the last week's discussion post, by the way. Our P naught was 0.14. We have our H naught, our H1 is P is greater than 0.14. So I'm going to go greater than and hit calculate. And we're going to use a 5% level of significance. This is like sociology stuff. That's typical, 5%. If no one tells you, you're using 5%, by the way. Okay, if it's just not talked about, that means they use 5%. Our test statistic is now Z because we have a sample size large enough. We have the number yeses was 163 and the number no's was 1,017 minus 163, which is what, 854, I guess. Both are bigger than 5. So that means we actually can use the normal distribution. And there's our test statistic. So then we can state there is statistically significant evidence to conclude that, and again, you want to look at H1, the population proportion of all Americans who think their home is haunted is greater than 14%. Or 0.14. You could also say there is statistically significant evidence to conclude that more than 14% of all Americans think their home is haunted. That's another way of doing the same thing. Okay. We can interpret the p-value, we can interpret the level of significance, but I wanted to really focus and let you know the conclusion is the most important. Okay, that's what you're going to do over and over and over again, not just in our class, but in the real world. The interpreting the p-value and the level of significance, it's important to understand it. But in terms of what you're going to be writing in articles and stuff, it's really the conclusion that's most important. And it's important that you know how to do that right. Any questions? Any questions? Okay, so we've now seen an example of hypothesis test for a mean with statistics, a hypothesis test for a mean with data, and a hypothesis test for a proportion. Those are the 3 main hypothesis tests this week that come up. We've also seen a left-tailed test, a right-tailed test, and a two-tailed test. This greater than is right-tailed because the greater than part on the number line is right. Less than is left-tailed because that's where the less than is on the number line. And two-tailed is not equal to because that's both sides. So just let you know that that's how you kind of think about it. So we've kind of seen kind of examples of each type. It is important that you can handle all of them. And it's important that you do the ordering that we did. I think I'm going to not do a whole lot more examples, but you can go example after example after example. The majority of people want to eat instead of drive while in a car. That's kind of an interesting little thing because there's self-driving cars now. Wouldn't it be better to like not have to worry about driving and just like sit in the back seat while your car drives itself and have lunch? Sounds fun. So again, this is that kind of stuff, and you can do a hypothesis test on that. So just to note, the word majority means greater than 50%, or P is greater than 0.5. Okay, any questions on that idea? Here's another example. Normal body temperature is 98.6. Hopefully you know that. That's normal temperature. Is the average different for marathon runners? So I don't know if you've ever run a marathon. I have, actually. And is it different? So if 38 marathon runners whose temperature was measured had a mean body temperature of 98.4 and a standard deviation of 0.7, what can be concluded at the 0.01 level of significance? Okay, so that would be a two-tailed test, and I want to show you some important words. I want to just kind of go over kind of seeing some of the important ideas. Different is one. Different means two-tailed test. That's a not equal to sign. So look for those key words. Any questions on that example? Okay. I want to mention one more thing I don't think I mentioned yet, is that after you've done the study. So for example, on, let's do the example, I typed it all out. Looking at the mean pH, we found statistically insignificant evidence to support the claim. After you do the study, you can revisit it and say, was a type 1 error or a type 2 error? Which one is now relevant? And are you really concerned about it or not that concerned? So in this case, we ended up finding insignificant evidence, which means that there is a possibility that we found insignificant evidence, but it really is different. The pH really is different. Okay? So that would be a possibility of failing to reject when you should have rejected. That's a type 2 error. So that means that there is still a possibility of a type 2 error, but there is no possibility of a type 1 error. Okay? Our p-value, on the other hand, was really large. It wasn't that close at all to even 0.1. If your p-value is really large, there is a possibility of a type 2 error, but it's not that high a possibility. Okay? There's a 0 chance of a type 1 error, but there's a small chance of a type 2 error. Any questions on that? So in this case, you probably wouldn't say, well, maybe I just need a bigger sample size and I should redo the study with a bigger sample size. You shouldn't redo the study with the same sample size over and over again, because then you'll eventually, if the null hypothesis is true, you're eventually going to be able to say that the null hypothesis was false and have a type 1 error, which would be terrible. So just let you know that. Any questions on that idea? Those are the things that you're going to have to do in the project, by the way. So you have to revisit the type 1 and type 2 error and decide which is significant and should you do another study? And if you think you should do another study, how big a sample size should you use based on the central limit theorem? A lot of details. Figure I should mention that. And I want to mention the secret word is hypothesis, because this week is all about hypothesis testing. So that word hypothesis is really important. Okay, I do want to spend a little bit of time talking about the project. So the first thing about the project is, let me go to the syllabus. And I want to remind you, again, a 25% penalty will be incurred on any student who cannot work with another student. Okay? You are allowed to use your same partners that you had on Project 1, but not required to. So if your partner's dropped, or if you didn't get along with your partners or didn't like the work that they did and you felt like you did all the work and they didn't do anything, then you're welcome to try and find another partner. And you could do that by going to the Project 2 discussion board and ask. Okay? So that's just a note about the projects. You need a partner. The second thing, it'll be about confidence intervals and hypothesis testing. It turns out it won't be the same thing we did this week and last week. It'll be what we're doing next week. And that is confidence interval and hypothesis testing, where you're looking at a comparison study between two different population means. Okay? It's very different than Project 1. Project 1 required you to survey people. Here, you're welcome to collect data, but you're not supposed to just grab someone else's study and look at that. Okay? You're collecting your own data, but you can so you can go to a supermarket and look at prices of a bunch of things at the supermarket, for example. Or you can go and, I don't know, measure the pH of a bunch of streams that flow into Lake Tahoe if you felt like it. Okay? It would take a lot of time, but it's a lot of fun because you go from stream to stream. It's very pretty. There's lots of things you can do to collect data. Just like before, if you can collect all of the data for the whole population, it doesn't work. You have to collect data that you really can only do a sample because the population's too big. It's a big note. Okay, it's too early to talk about the details because we don't know about hypothesis tests and confidence intervals for comparing two different data sets. That's next week, but I want to give you just kind of a flow of the project. Also, the same timeline idea should happen for project 2 that happened for project 1. Step 1 is get a partner. Step 2 is post your idea on the project 2 discussion board. That idea should involve your null and alternative hypotheses and your survey question that you're going to be asking, or it doesn't have to be a survey question. It could be how you're collecting the data. And again, it better be 2 data sets. And we'll talk about the different types that you're allowed to do. But that's next week, so it's too early to actually do it right now. And then the next step is to put in the computer in the spreadsheet, which I'll show you next week about how to do that. And then after putting it in the spreadsheet, you do a draft write-up. And then after doing the draft write-up, you're going to be hopefully sending it to me at least by Thursday at 8 a.m. before it's due, but better is days before that, which isn't for more than 4 weeks, but still, don't wait till the last minute. Don't do it this week, but you should really be starting it, maybe next week is the idea. Okay, and by the way, the webinar next week will be Tuesday, not Monday, because Monday is a holiday, and again, holidays are important. I don't give webinars during the holiday. I don't even have office hours. That's a holiday. I might answer questions on email or discussion posts, but no time things. So that's just a note. It'll be on Tuesday, and that's why we did 2 Mondays in a row this week, so that we can do Tuesday next week. That was the reason to make it work. So that is the plan, and then of course the final step in the project is to address all my comments, and then and then submit it into Canvas. Do not wait until 11:59 p.m. on Sunday. A few of you actually thought about doing that and then actually couldn't submit it at the very last moment and had to submit it late, and I did take off points. So don't wait until the very last minute. That's a mistake, just a note. One more thing is, just like project 1, you have to have at least a supposed client. And the project's going to be all about talking to the client. So that's pretty much it. Again, I hope you have a great Memorial Day weekend. And as always, I'm going to stop the recording, but then answer questions for those that are here. And hopefully it'll all go well. And I'll be checking the Q&A board and the project 2 discussion board and look at my email, all that, for any questions you might have. So let me stop the recording.